Hello guys, welcome to my YouTube channel. In this video, I will try to explain you the complete math behind support vector machine, how it will come up with a large margin so that there will be a better clear cut difference between positive and negative examples. Okay. So if you guys have not watched my introduction to support vector machine, please go and watch it so that you will be able to understand why I am explaining how it is considering the large margin. Okay. So let us start. So before starting, if you guys haven't subscribed to my channel, please do subscribe. It will help you to learn a lot of things. I am explaining each and every algorithm in depth with math intuition. Okay. So let's start with SVM now. So as you guys know, SVM comes up with some support vectors and then it will build a decision boundary so that the distance between the support vectors is maximum. Okay. So I have represented this in a pictorial way here. So if you guys can treat these two things as support vectors, there can be more than one support vector on each side. Okay. So for our easy understanding purpose, let us consider only one at each. Okay. So let me mark this as x1 and mark this point as x2. Okay. And this is my decision boundary. Okay. And this particular distance is called as margin. And support vector machine, with respect to support vector machine, we want this margin to be as large as possible. Okay. So how does it work? So if you guys have seen my logistic regression video, we can understand that this particular decision boundary, theta transpose x, if we make this line to pass through the origin, so that in the equation y is equal to mx plus c, this c will be, this is the intercept, right? So this will be 0. So just I am representing theta transpose x is equal to 0. Okay. So this is the equation of decision boundary. So at this side of the decision boundary, we will have negative examples and we represent negative examples with -1. And below this line, we will have positive examples and we represent positive examples with +1. Okay. So please keep this in mind. So in the same way we have represented the equation for decision boundary, we will represent this particular margin, right, with the equation which will be represented as theta transpose x is equal to -1. And in the same way, the equation of this particular side of the margin will be theta transpose x is equal to +1. Okay. And now we want the distance between these two stuffs to be maximum, correct? So how do we calculate the distance? So it is nothing but theta transpose x1, right? This is x1 because this point is x1 and this will be x2 because this point support vector is x2. Okay. Theta transpose x1 is equal to -1. Theta transpose x2 is equal to +1. So we want the distance between these two stuffs to be maximum, right? So if we subtract these two equations, this is just a linear algebra, right? So this is the high school stuff that we all have learned. So if we simplify this, we will arrive at this particular equation. Theta transpose will be a common. X2 minus x1 is equal to +2. Okay. Now I want the distance between this x2 and x1 to be maximum. So in order to do that, I have to do away with theta transpose. So how can I do this? This is a vector. Okay. So let's consider theta 1, theta 2. Theta 0 equal to 0 and we are dealing with two features. Okay. Now if this is a vector, it will have some direction, right, and magnitude. So we have to do away with this. We have to do away the magnitude part of this particular vector. So how we can do that? With the help of linear algebra, we all know that if we divide both sides of the equation with norm of this particular theta, we will do away with the magnitude, right? So if we do this, the next resulting equation will be x2 minus x1 is equal to 2 by norm of theta. Okay. So this one we have to maximize. Support vector machine will maximize this particular stuff. Okay. So in other words, in order to apply gradient descent, right? So we always deal with the convex function, correct? And we minimize the cost function, and we always deal with minimization problem, right? So in order to be consistent with gradient descent, what we can do is we can flip this equation. Without instead of maximizing, we can minimize 1 by 2 times norm of theta. Okay, so this is what we will be doing with support vector machine. If we do this, we will have this large margin separation between the support vectors that decides the decision boundary. Okay, so now we will see how do we represent the cost function of support vector machine. Okay, so in order to understand that, let's go back to logistic regression. Okay, so logistic regression. So we have two separate cost function, right? If y is 1 belonging to positive class and y belonging to negative class, right? So that is, if y is belonging to positive class, the cost function is given by 1 by log into 1 by 1 plus e power minus theta transpose x, correct? And this one in a graphical way is represented like this, correct? So 0 plus 1 plus 2, this is our z, right? Minus 1 minus 2, and this will be exactly 0.5. Okay, so if you guys have not seen my logistic regression video, I will suggest you to go back to logistic regression video, understand the cost function, and come back here. Okay, so now with respect to support vector machine, what we do, instead of having cost function like this, we will have a cost function something like this. So it will be 0, it will be parallel or almost aligned to the horizontal axis from starting from plus 1, but instead of the curve, we will get some straight line like this. Forget about the slope of this particular line for the moment. Okay, we are not concerned with the slope to explain this particular process. Okay, this is when we have y associated with positive class, positive example, right? So this particular red line here is the cost function for SVM. This will be for logistic regression. And the equation is minus log hypothesis, right? And hypothesis is given by 1 by 1 plus e power minus theta transpose x. Now, when y is belonging to negative example, so what is the cost function for logistic regression? It is minus log of 1 minus hypothesis, right? Correct? And this, in a visual way, we can represent it like this. Okay, so 0 plus 1 plus 2 minus 1 minus 2, and this will be exactly 0.5. Now this is with logistic regression when we have negative example. What happens with respect to support vector machine? The same cost function will look something like this. We will modify this cost function in such a way that it will be aligned to the horizontal axis starting from minus 1 towards the more negative side, and then we will have the straight line like this. Okay, so this is how the cost function for SVM looks like, and this is for logistic regression. Okay, now this particular cost function, what we have seen with respect to SVM, is also called as hinge loss. Okay, so hinge loss, and this can be given as 0 if y into theta transpose x is greater than or equal to plus 1. If otherwise, it will be 1 minus y into theta transpose x otherwise. Okay, so this is what hinge loss looks like, and this will be the loss function that we will be making use for our SVM. Okay, now in order to understand how this comes up with a large margin, okay, so we will have to understand the theta transpose x. Okay, before going to large margin classifier, we will write our cost function for SVM. So how we can write that? It is 1 over m summation I is equal to 1 to m. Okay, this particular stuff will be yi into cost of 1 is theta of x, okay, plus 1 minus yi into cost of 0 s theta of x. Okay, plus whatever we have arrived at this particular point, right? We have to minimize 1 by 2 over norm of theta, correct? So we will add that 1 by 2 over norm of theta. Okay, so this particular stuff here is our cost function for support vector machine. Okay, and this cost 1 and cost 0 here you can replace it with this particular stuff here. Okay, you can just replace that. So this is how the cost function for SVM looks like, and there will be another term that we will introduce here and we call it as C. Okay, so what is this C? C is something you can think of it as the number of errors that we allow. Okay, so why we are allowing the errors? So this is just a hypothetical case, right? We will never have the data points which can be perfectly separated in this way, right? Positive and negative examples in a clear cut way. There will be definitely many overlaps within the data points, correct? So in that case, we will allow some errors, some points to be misclassified, okay, in order for us to have the generalized model. So we do not want to overfit the data, overfit the training data, right? But instead we want to have the generalized model. So in order to come up with a generalized model, we will arrive at, or we will allow some errors within our model. We will allow misclassification. Okay, so that's what this particular C deals with. Okay, so now that you have understood the cost function, we will understand how this SVM will arrive at the large margin. Okay, remember our aim is to minimize over theta. What we have to minimize? Basically we have to minimize this plus C and this term A. Okay, I just wrote it in a short form. So C and this whole term I have written it as A. Okay, so just remember this particular stuff, we have to minimize this. Okay, so now in order to understand this, let us see what theta transpose x looks like. Okay, so this is called as vector inner product. Vector inner product. So how we can visualize this? So let's say I have my theta and x. Okay, this is my theta. Let's say it is theta 1. The coordinates are theta 1 and theta 2. Okay, and let's say I have my x here. X, the coordinates are x1 and x2. Okay, x1 and x2. Now, if I take the orthogonal projection of this particular x on this particular theta, right? Orthogonal projection. When I say orthogonal, the angle of the projection is 90 degrees. Okay, and the length of the projection I will consider it as P. Okay, the length of the projection of x onto theta I will consider it as P. Now this theta transpose x can be given as P into norm of theta. Okay, now this norm is also called as length, right? In other terms it will be a Euclidean length. Okay, so what is this Euclidean length? How we can represent this? So length of theta can be written as square root of theta 1 square plus theta 2 square, correct? So this will be the norm of theta, right? In other words, if we expand the theta values, theta 0, theta 0, let's forget about theta 0 now. We will deal with theta 1 and theta 2, and x will be x1 and x2. Okay, so these are our coordinates. So theta transpose x will be theta 1 x1 plus theta 2 x2, correct? So we can prove with the help of linear algebra that this length of the projection multiplied by norm of the particular vector theta will be equal to theta 1 x1 plus theta 2 x2. So these both are one and the same. Okay, we can prove this with the help of linear algebra. So we do not need to go into the in-depth mathematical proof of this particular equation, but you can just take my word for this. Okay, we can just understand in this way. If we just assume or if we just accept that with the help of linear algebra, we can prove P, the length of the projection of x on theta multiplied by norm of the theta, will be equal to the theta transpose x, that is theta 1 x1 plus theta 2 x2. Okay. Now remember, we are minimizing j is equal to 1 to n theta, right? Or in other words, there will be 1 by 2 here, correct? Theta j. Okay. So this we have to minimize. We have to arrive at some small values of theta, right, in order to minimize the overall cost function. Now, if you check this particular step, we know that theta transpose x must be greater than or equal to plus 1 for positive examples, right? Positive examples denoted by plus 1, okay? And this theta transpose x needs to be less than or equal to minus 1 for negative examples, correct? And negative examples are denoted by minus 1, right? With respect to SVM I am talking about, right? So this is our main condition. So if you just substitute this P into norm of theta, right? So theta transpose x can be written as P into norm of theta, correct? We want this to be greater than or equal to plus 1, okay, with when we have positive examples, okay, and we want P into norm of theta to be less than or equal to minus 1 if we have negative examples, okay. So this is what we have to do. Since we are minimizing the values of theta in order to minimize the cost function, if we get this as a small number, right, small number, okay, in order to achieve the product of P into some small number greater than plus 1, we want P to be large, correct? So if you apply the same logic with this particular equation as well, we will need P to be some large negative value. So in this case, we want this to be large positive value. In this case, we want this to be large negative value. So now if you look at this particular graph here in above, this particular distance is d minus, this particular distance is d plus, distance with positive examples, distance with negative examples. So we want this d minus to be large negative value which deals with P. In case of the equation P norm of theta less than or equal to minus 1, okay, with respect to negative examples. So similarly, for the positive examples, we want P into norm of theta to be greater than or equal to plus 1, correct? Right? So, but since we are minimizing the theta, minimizing the cost function over theta, we need some large positive value with respect to P so that we can have the overall value greater than or equal to plus 1. Okay. So, this is how SVM comes up with the large margin classifier. Okay. So, if you want to visualize this, if I draw some data points, okay. So, let me just explain it to you guys how the projections work. So, let's say I am having some data points here. Okay. Forget about positive negative placements, just understand the projection values. Okay. If I come up with this particular decision boundary, the projection of this, right, on top of this is the decision boundary, right, and the theta will be perpendicular to this, right. So we have to come up with a large margin such that the margin between this positive and negative examples both are maximum. Okay. So if you just go with this particular decision boundary here, we can come to know that the projection of this, right? So theta transpose x. So if you project this onto this particular theta, this particular projection is very small, right? Right? So this particular decision boundary will not be suitable with respect to support vector machine. So what support vector machine chooses? Let's say we choose a decision boundary like this, And with the help of linear algebra, we can show that the theta will be perpendicular to the decision boundary. And now the projection of this particular point, this is the length of this particular projection, right? So this is the length of this particular projection. This will be large compared to earlier decision boundary, correct? So this is how we come up with a large decision boundary, okay, large margin with respect to decision boundary when we are dealing with support vector machine. So hope you guys understood this. If you guys have any, there is a lot of maths involved in this. I have tried to explain to you in a simpler terms by combining many stuffs. Okay, I have gone through many videos and many stuffs I have referred so that I can explain it in an easier way. I know still this is a lot to consume. You guys may have to watch this video multiple times in order to understand. And if you still guys have any questions, please reach out to me in comment section, or I'll try to simplify it further and upload a new video in order to explain this in an easier way. Okay, so try to understand this. If you guys have not understood, please reach out to me in comment section. I'll try to get back to you with answers. Till we see you in the next video. Happy learning. Bye bye.